Hello everyone. So today we're going to continue on our discussion on green theorems. So last video we get to state what the green theorem is. So green theorem basically allow us to rewrite a closed curve integral along some boundary of some regions into a Riemann integral. So once again, the important part here is that it allows us to turn a single integration, a line integral, but for two different differential, and rewrite that into a double Riemann integral, which basically means I can now integrate directly with dx and dy together. So that's the important part of it. So show you how this theorem works by giving you an example to illustrate how to use this theorem, by showing you what happens if I use this theorem versus when I don't. How to evaluate closed curve integral properly. So here's the formula. So I'm going to hope to try to keep that on the top of the screen for a little bit, but depend on how much room I need when I do the problem. So here's the example. Let's say we let alpha be the closed curve given below. So what is alpha? So alpha would be this. So here's my xy plane. Here's the point 0, 0. And here's the point 1, 1. And alpha travel along the curve y equal to x squared to go from 0, 0 to 1, 1. And then travel back to 0, 0 through the straight line y equal to x. So here's what alpha look like. So alpha is this loop that go around from 0, 0 to 1, 1, then back to 0, 0. And what I'm going to ask you to do is I'm going to ask you to do the following. I'm going to ask you to find this closed curve integral of alpha xy dx plus y squared dy. Okay. And I'm going to ask you to basically do it two ways. A, just using line integrals, and B, apply green theorems. Okay, so let's go and try to find this line integral. So before we actually get started, do understand the following. This integral right here is actually the same as this one, just written before the dot product. And in this expression right here, this is my vector f, this is my d vector x, and we have a dot product between them. So make sure you understand how to read the questions. So as a matter of fact, written this way, xy dx plus y squared dy, I actually did the dot product for you already. Okay, so actually I'm trying to be nice. Now let's try to do A. Let's try to integrate or find this line integral using just line integral. Just using line integral, evaluate it. So the way to do that is the following. Since I do know the relationship between the two equations, between y and x for the closed curve, I can do the following. I'm going to separate this into two alpha 1 and alpha 2. And I'm going to try to simply calculate the line integral for both of them and then see what happens. Okay, so let's start with alpha 1. So alpha 1 is basically mean that y is equal to x squared. So therefore, my closed curve integral, well actually I don't have a closed curve integral if I'm just doing alpha 1. So I'm going to have a line integral alpha 1 of xy dx plus y squared dy, which is simply equal to the integral. Notice that if y is equal to x squared, then dy must equal to 2x dx. So therefore now I can actually change my integral into just x and dx by saying this would be the same as the integral from 0 to 1. That's the x value go from 0 to 1. X times x squared dx plus x squared times 2x dx. So just a little bit of cleaning up to do, but it's not too bad. So I'm going to go and clean it up. So that would be integral from 0 to 1. Would seem to me is x to the third plus 2x to the fifth dx. So therefore become 1/4 x to the fourth plus 1/3 x to the sixth. You vary from 0 to 1, so that just become 1/4 plus 1/3, so that would be 7/12. So that's pretty good. Now for alpha 2 is a little tricky. The reason why for alpha 2 that's a little tricky because if I replace y equal to x and y and dy equal to dx, that seems like exactly what I'm supposed to do with alpha 1, but there's a problem. The problem is that that integral would go in the wrong direction unless I use the limit correctly. So in here, important to understand is that this would come out to be this. So there will be line integral alpha 2 xy dx plus y squared dy. So that would actually equal to integral from 0 to 1 x times x dx plus x squared times dx, but I have to introduce a negative in front of it. The reason why, because without that negative, I'm actually evaluating the line integral over alpha, but in the opposite direction, meaning it will go from 0, 0 to 1, 1. So with the negative, that will allow me to actually calculate the opposite of this curve. Now, some of you might be thinking, can I just go from 1 to 0? Yes, you could, but you really wouldn't write an integral where the lower limit is bigger than the upper limits. And when that's the case, what you want to do is reverse the limits. And when you do that, you have to introduce a negative in front. That's exactly what we have right now. So keep that in mind. So if I don't have the negative, then it would be for alpha 2 the way it is. But with the negative, then that would be basically be the curve go from 0, 0 to 1, 1 along the line y equal x, but then negation of that. So once again, it just require a little bit of cleanup to do. So that just equal to negative integral from 0 to 1 x squared, 2x squared actually, dx. So that just become 2/3 x to the third. You vary from 0 to 1 with a negative in front. So that just become negative 2/3. So that's not too bad. And now combine the two together. Now I can say the closed curve integral of alpha xy dx plus y squared dy must equal to the integral of alpha 1 xy dx plus y squared dy plus the integral alpha 2 xy dx plus y squared dy. And therefore that would be 7/12 plus negative 2/3. So negative 2/3 is negative 8/12 plus positive 7/12 become negative 1/12. So that would be our answer using line integral. And notice that does require me to set up two separate integration to do, and also have this problem that when I do alpha 2, I do have to account for this negative. So once again, if you don't want to use a negative, you could just say from 1 to 0 instead of 0 to 1. I just like to always write my integral using a lower limit that's smaller than upper limits. That's just how I always like to do my integration, to keep it things make sense for me. And so if I do that, I would have to have a negative in front to balance out the flip-flop of the orientation of the curve. So that's pretty straightforward. So now the question is, what happened if I were to apply green theorems? What would happen to if I apply green theorem? So, well, let's see. Oh, well, actually, you know what? That's not B. That's still A. All right, so now let's try to do green theorem and see what happened. So we're going to apply green theorem. So what is the green theorem formula? It say that when I integrate over dd, f1 dx plus f2 dy. That become a double Riemann integral over d of df2 over dx minus df1 over dy dA. So in our case, in this particular example, our f1 would be xy, and our f2 is actually going to be y squared. So because of that, I can now define df2 over dx minus df1 over dy. So therefore will be d over dx of y squared minus d over dy of xy. So that come out to be 0 minus x, so become negative x. So that become our integrand. So now I'm ready to integrate this. So Green theorem say that if I take the closed curve integral of alpha of xy dx plus y squared dy, that's the same thing as a double Riemann integral over d of negative x dA. So that's just a very typical double Riemann integral. So now I can just try to integrate this. So in order to integrate this, I have to pick an order of integration. So notice that in this particular case, the boundary of our regions D is given using y equal to. So I'm more inclined to do dy than dx. And if I do that, my integral actually work out to be something like this. Integral from x equal to 0 to x equal to 1. Integral from y equal to x squared to y equal to x, negative x dy dx. How to set up a double Riemann integral over a two-dimensional region of integration on the xy plane is something that you learned back in chapter 7, 2 chapters ago. You should not have any issue figuring that out. Now what I'm going to do is going to integrate this. So if I integrate this, I'll have integral from x from 0 to 1. Integral of negative x become negative xy. Evaluate from y equal to x squared to y equal to x dx. So that become integral from x from 0 to 1. That become negative x times x, which is negative x squared. Minus negative x times x squared become plus x to the third dx. And so that come out to be negative 1/3 x to the third plus 1/4 x to the fourth. Evaluate from 0 to 1. That become negative 1/3 plus 1/4. And so common denominator is 12, so it become 12. Negative 4 plus 3. So that would be negative 1/12. Notice it match our answer as it should. Remember what I said, the line integral, the value for the line integral should not be dependent on the way we calculate it. Okay, and if it does, then that will mean that something is not consistent and the whole world will fall apart, and we don't like that. Now let's look at another example, and that will probably be the last example I want to show you for green theorems, and if we have time we can go through more example during class if you need me to go through more example with you. So here's the next example. Let's C be the boundary of a square with vertices 1 1, negative 1 1, negative 1 negative 1, and 1 negative 1 as given below. So here's what C look like. So C look like this. Here's 1 1. Here's the point negative 1 1. Here's the point negative 1 negative 1. And here's the point 1 negative 1. And then C will look something like this. So notice that in this case, the orientation of the curve does keep the region bounded by on the left. Okay, or if you think about the closed curve of an orientation that's counterclockwise, just like this one right here. Okay, we go around like this direction. Okay, that's the orientation. And now let's say I want you to find this line integral. We're going to let vector f of xy equal to negative y e to x, x e to the y. I'm going to go and ask you to find me this closed curve integral over C, f dot d vector x. Now, without using Green theorem, to try to evaluate this line integral will actually require me to split it up into 4 integral individually. Okay, so this is basically what C look like. Oops. The path C. But to evaluate it properly, I would have to separate it into, let's say, C1, C2, C3, and C4, meaning I have to actually do 4 separate line integral to calculate this closed curve integral. Now granted, they shouldn't be too hard to do. The reason why they shouldn't be too hard to do, notice that we talked about this back in chapter 8.1. If we have line integral where the line actually go parallel to the coordinate axis, it makes it extremely easy to do, because meaning that one of the variables must be constant. So therefore, still allow us to actually reduce our line integral from multiple differential to a single differential. But still, it still requires me to do 4 separate line integral. Lucky for us, we learned Green theorem. So we're going to go ahead and use Green theorem to help us out. So in here, the first thing I notice is that our f1 is actually negative y e to the x, and our f2 is actually x e to the y. So therefore, our df2 over dx minus df1 over dy simply equal to e to the y minus negative e to the x will become plus e to the x. Remember, when I differentiate f2 with respect to x, e to the y is a constant. So therefore, it just basically constant times x. So the derivative just becomes the constant. And same thing happened to df1 over dy. So now I can actually integrate it. So therefore, the closed curve integral over C of f dot d vector x, or actually maybe I'll write it this way, of negative y e to x, x e to the y, dot product dx d and comma dy, is basically equal to a double Riemann integral over, I don't know what I'm going to call the inside region. We're going to call it R. Of R of e to the y plus e to the x dA. Now, because this regions R is actually a rectangular regions, so therefore make the integrating it a lot easier to do, and also make the decision of whether we integrate dx dy or dy dx a really non-issue, because it doesn't really matter. It's all constant anyway. So I'm just going to say, I don't know, dx dy, because since the last problem we do dy dx. So I'm going to say this is the same thing as the integral. I say dx dy, right? So I'm going to say y e to the y plus e to x dx dy. So x would go from negative 1 to positive 1. And guess what? Y also go from negative 1 to positive 1. Because those are the 4 lines that bounds these rectangular regions. So now it's just a matter of, I guess, evaluating this or integrating this. So let's go for it. So that would equal to integral y from negative 1 to positive 1. Integral of e to the y plus e to x dx become x e to the y plus e to the x. Evaluate from x equal to negative 1 to positive 1 dy. So when I plug in negative 1 and positive 1, what I get would be this. That would be integral of y from negative 1 to positive 1. When I plug in 1, I get e to the y plus e. minus, when I plug in -1, I get negative e to the y plus e to the -1 dy. Oops. So seem to me that the e to the y actually combine, and so become 2 e to the y, and then I have plus e minus e to -1. So I can now integrate this. So when I integrate this with respect to y, I get 2 e to the y plus e times y minus e to -1 times y. E value from y equal to -1 to y equal to +1. So go ahead and plug in 1, I get 2e plus e minus e to -1. Minus, when I plug in -1, I get 2e to -1 minus e plus e to -1. So if I distribute everything correctly, seem to me I have 2e plus e minus -e, so become 4e. -e to -1 minus 2e to -1 and minus e to -1 become minus 4e to -1. So therefore that comes out to be 4e minus 4 over e. That's my line integral. So that's not too bad. And definitely a lot quicker than doing 4 separate integral, even though those 4 integral might be simple to do, but still going to take a long time to do. So that's actually the last example I want to show you. So the last thing I want to talk to you about is the following. Both of the integral that we just did, both example that we've done, are both from simple regions. So what happens when we have a non-simple regions? How do we actually deal with that? Well, actually pretty simple. So for a non-simple regions, we can actually divide it into disjoint, meaning non-overlapping, disjoint simple regions. Then applied Green theorems. To evaluate each of the simple regions. Now, one thing that's students often get worried about is when you divide the regions, what happens is the following. Imagine the following example. Suppose I have these regions right here. And this is alpha. And okay, just assume that all these lines are either horizontal or vertical. And here's regions R, basically, this whole thing. Now, of course, this is a non-simple regions because if I draw a horizontal line, you can notice that on the top part, I would actually intercept the boundary 4 times. So therefore, it's not going to work because it's not simple regions. But lucky for us, I can actually separate this into multiple smaller simple regions. As long as they don't they're disjoint, so that means they don't overlap, I can still get the same result. But how do I separate them? Well, the way to separate them is the following. Is by introduce a boundary right here, or actually maybe I do it this way. And right here. Or technically speaking, you can also do right across here and here to split into 3 different regions, but I choose to do this one right here. Or actually, you know what? How about we do a combination of the 2? I split this one this way. So if I do that, what happen is I actually form 3 separate regions. So now I'm going to try to draw it out for you so you see what's the issue here. So here's the so I kind of pull them apart, and now I'm going to use a red line to kind of connect them, to close them off to form my enclosed region. So now I have, let's say, R1, R2, and R3. The interesting thing about this particular separating a region to smaller regions is the following. In order for it to actually work, I do have to add in some boundary. So if you look at the picture on the screen right now, the red curve, the red line are what I have to add in to complete each of the regions. Otherwise, they would not be enclosed regions. So one thing that's the thing about is, wouldn't that create longer boundary? Because if you think about these two pictures, you can see clearly R1, R2, and R3 would have a longer perimeter, which is basically what the closed curve would be, compared to R itself, because I have to add in those red lines. So wouldn't that change the value of the line integral, because line integral is dependent on the curve? And you'll be correct. It should, but it wouldn't. Why not? Because of following. Notice that every time when we separate a region into two, I have to add in not one, but two curve. Because when I pull the regions apart, both regions will require a boundary to fix to make it enclosed. So therefore, I do not add in one curve, but I always add in two, a pair, if you would. More important is also notice the following. Look at R1. If I add in this red line must be going in this direction to fit into the boundary for R1. But the same exact line that pull off from R2 would be the same exact curve, but go in the opposite direction to fit into the boundary R2. And if you remember Theorem 9.1.1 state, if you have two boundary or two curve, but go in opposite direction, they will yield opposite line integral value. So therefore, adding these two boundary together, even though exactly the same curve, but they go in opposite direction, the line integral value would be 0 when I combine them together. So technically speaking, adding one line and then adding this one boundary for R1 and the boundary for R2, because they're going opposite direction, they just balance each other out. And if you look at the boundary from R2 and R3, is the same exact concept. They must go in the opposite direction. So therefore, when I put these three regions combined together, those pair of red line that I put together will just cancel each other out and disappear, which is why allow us to form the regions R, a non-simple regions. So what does this tell me? What does this tell me that in the case of a non-simple regions integral, like in this case, when I look at alpha, closed curve alpha of f dot d vector x, I can say this is the same as the regions R of df2 over dx minus df1 over dy dA. And because R is the same as the union of R1, R2, and R3, I can say this just equal to Riemann integral R1 plus the Riemann integral over R2 plus the Riemann integral over R3. So therefore allow me to split the regions R into three separate Riemann integral and then evaluate each one individually. And that is actually the last thing I want to talk to you about in 9.1 green theorems. So as I say, if you feel like you want me to go for more example on using green theorems, we can definitely do that in class. All right, and that will be it. I'll talk to you next time. Okay, bye-bye.